So we will come to the next presentation. The next presentation presents the chapter 11 of part 5, and the chapter 11 contains underground structures. The presentation will be given by Professor Pitilakis from the Aristotle University in Saloniki. He's actually the president of the European Association of Earthquake Engineering, and he was highly involved in the evolution of the part 1 and part 5. And he was the president of the Greek Society of Earthquake Engineering, and he's also has also teaching obligations at the Tongji University in Shanghai, and he's really one of the leading experts in soil dynamics and geotechnical engineering. And yeah, I'm happy to introduce his talk about underground structures, and I will lead over the floor to Professor Pitilakis.
Thank you. Okay, so this is a bright new section. It is a completely new. It is not the evolution of the previous one. This section is limited to the determination of the actions and does not cover design verifications. This is very important, and for this reason, you will not see so many equations, expressions, and discussion, because it will be concentrated only on the principles and the basic philosophy of the design of underground structures. It covers these sub chapters, the general one, okay, then the seismic actions, the methods of analysis, quite general, the seismic loading. The first two are for the tunnels. The third one is for large underground spaces like parking and metro stations, which were not covered so far. And we have a small chapter at the end for the culverts. So we believe that we cover the most part of what an engineer is needing. And there are 3 annexes. At the beginning, it was 5 or 6, but we reduce it, all informative, in order to provide simplified evaluation of peak ground motion for the seismic design of underground structures, simplified analytical expressions for seismic tunnels, and impedance functions for underground structures as well. We will discuss about these issues during the presentation. Now, the tunnels and underground structures shall be designed to provide seismic performance consistent with the limit states that we have discussed a lot before. And of course, the associated seismic actions. They should be designed against ground shaking and permanent ground deformations. For ground shaking, the problems are not so important, but for the permanent ground deformations, we will see that in most cases, the code has the tendency to say, if you can avoid it, please do it. Sorry. Now, an important issue which may affect the design of the tunnels is that it is set in a very strict way that tunnels and other underground structures should be primarily designed to accommodate transient and permanent deformations. Why? Because the imposed ground deformations on underground structures are more important than transient seismic loads related to the inertia values. And then it is also said, something that is also said for the pipelines, that spatially extended underground structures, in this case, seismic design in the transverse and the longitudinal direction should be considered with the spatial variability of ground motion and the associated phenomena. Soil structure interaction effects should be considered according to what has been discussed before by George. And regarding the seismic earth pressures, it will be according to what will be discussed after my presentation by Luigi. Seismic actions. Due to ground shaking, after adjustment, we say accounted for the depth and the dimensions of underground structures and the spatial variability. In the Appendix A, we provide some guidance on the estimation of the ground motion. I'm not going through the detailed presentation of what is in the annexes, because it will take a lot of time to somehow explain, and so with the time that are allowed for this presentation, it would be impossible. For active faults, potential active faults are defined with what has been already said in part 1 and in this part 5 as well. And we say that the necessary parameters that should be estimated, it is the angle of incidence, the dip, and the offset at the location of the structure. In case of precarious slopes and the problem that may face on the tunnels and culverts, the most important issue is that we have to be able to estimate the permanent slope displacements. And the tunnel should be designed for these permanent slope displacements. And if it is impossible to accommodate, we should avoid this place. This is the basic idea for this design. Underground structures in potentially liquefiable soils, more or less the same as previously for the slopes or the faults, but in cases where it is not so critical and you may be able to build a tunnel in a liquefiable soil, then you have absolutely to take into consideration the buoyancy effects. But there is a general clause saying that sites susceptible to hazards such as active faults, precarious slopes, liquefiable soils should in general avoid it, unless specific design and construction actions reducing the risk to acceptable limits are adopted and made. Ground motion parameters. Ground motion parameters should be established for the seismic design of tunnels and underground structures, with this, let's say, difference between low and moderate seismic actions and strong ground motion cases. Now, if we are in the case of low to moderate seismic action classes, then we can use the peak ground motion parameters, PGA, PGV, or the displacements. But the problem is that we have to establish, to define, and to estimate these values in a proper way. So the design response spectra should be also consistent with these parameters. However, for the evaluation of the parameters of ground surface, various depths of the embedded structures, and at the depth of the base of underground structures, it is something that the designer should take into consideration. So we say that in most cases, a ground-specific response analysis may be carried out in order to estimate the appropriate figures that we have to use in these cases. For moderate and high seismic action classes, it is necessary to make a ground-specific response analysis for the total length of the structure. So we say that for moderate and high seismic actions, a ground-specific response analysis should be carried out. There are some proposals for the low seismic actions on how to estimate the variability with depth. A strong discussion in the committee has been made regarding the values that we could use for the PGV and PGD because they are necessary and the variation with depth. And finally, we prefer to remain to what is proposed in part 1. And so there are some correlations there and could be used. In any case, in Annex G, you can find simplified expressions and empirical relations regarding this issue. So it provides all this, including some recommendations and guidelines for the spatial variation and the incoherence of ground motion, something that is also discussed a lot in the part of the silos and the pipelines. For the seismic action in the longitudinal direction of the tunnels, it is necessary to use an apparent velocity, as it is described both in the annex, but also in the way that these issues are addressed in pipelines as well. We say in this case that in the absence of site-specific studies, which are rather rare, I must admit, the apparent velocity may be taken equal to 1,000. This is more or less what is proposed in the United States, and we do not have other arguments in order to modify this. It is a longly debated issue, but it is believed that this number, 1,000 meters per second, is a reasonable one. For seismic faulting, seismically triggered landslides or liquefaction, the permanent ground displacements, as said, must be estimated, and these are the way. And this is the way that this structure should be designed. Of course, we should take into consideration that these values have been estimated for the design return period and the category of structures under consideration. Methods of analysis. For the seismic design of underground structures, the transient effect of the seismic action may be expressed either in the way of forces in the transverse direction or ground deformations in both directions. The effect of seismic action due to permanent ground deformation should be expressed exclusively in terms of displacements. Now, an important note is that we can use the seismic earth pressure acting on the structure in the transverse direction. However, we must be quite careful about using this because the methods, as will be described in the next presentation, should be used with a certain precaution. And in general, it should be used for shallow tunnels, cut and cover structures, etc., not for deep structures. Because for deep structures, if we are using the formulas or the expressions that will be presented for the retaining structures, it may involve huge uncertainties. And so methods that are mostly referred to this clause should be used instead of using the more classical one that maybe is used till now on the application of seismic earth pressures. Now, the analysis method should be based on the main dynamic response patterns of the structure. And the main deformation modes in the transverse response is the ovaling and the racking response. These are among the 3 or 4 only figures that I will present. This is the ovaling situation, and this is the racking and the rocking. In some previous international codes, there were only the racking effect, which is actually a shear deformation of this kind of structures, which is applied also for underground spaces. But recent studies, not only here but in other parts of the world and other people, have seen that in many cases we have a kind of rocking, and so the analytical expressions and the way to estimate the internal forces in this kind of situations are considering these effects of both racking and rocking. Now, ground deformations in the transverse and longitudinal. We can use closed form solutions without considering with or without considering solid structure interaction, or we can go to advanced numerical methods, 2D or 3D, and we say that this is preferable for high seismic action classes. In Annex 8, we provide expressions for the closed form solutions, which could be used in many cases, at least for the preliminary analysis and not only. If when soil structure interaction is ignored, it may assume that the free field ground shear deformations along the depth of the tunnel are directly applied statically to the lining to compute the seismic loading. And again, in Annex 8, we provide some guidance for the calculation of the internal forces. If we have to use soil structure interaction effects for both circular and cut and cover structures. Simplified analytical expressions accounting for the relative flexibility of the structure and the soil may be used, and we provide in Annex simplified expressions. In particular, for the cut and cover regular tunnels, this is based on the so-called flexibility ratio related to the surrounding soil. It is a methodology that is used for several decades now. It has been somehow improved and updated, but the essential is the same. And in Annex 8, we provide the guidance for these methods. The basic idea can be seen in these two figures. Okay, you have the structure, and you can model it with soil springs, how soil springs are estimated. We give some guidance, but the general philosophy, when we consider soil structure interaction, has been discussed by George before. We can apply either displacements or pressures, which should be estimated in the way that is described by George before. What is important here is to have to take into consideration the friction forces, the forces also around the perimeter structures are embedded, the type of the underground structure, the deformation modes, and the seismic strain amplitude for the design ground shaking and the soil. We provide the guidance for the calculations of this. And I must say at this stage that there are quite a lot of uncertainties behind the estimation, but we decided to give some guidance. Okay, so we must be very careful for the estimation of the spring values, I mean the stiffnesses, and as I said in the previous slides, I described more or less what is included in the annexes. Now, we say that the seismic analysis in the longitudinal direction of long underground structures, when soil structure interaction are accounted for, the analysis may be based on the beam on dynamic Winkler foundation approach, with a selection of appropriate values for springs and daspots, and take into consideration the tangential and normal soil structure interaction. Again, the values of the springs is longly debated. We are proposing some numbers as the way to estimate, but again, we say that the engineers should be very careful because the uncertainties may be quite high. And this is said in Annex I, which provides the guidance for the calculations of the springs and the dashboards. We put also a general comment saying that don't worry very much about soil structure interaction effects in the longitudinal direction, at least, because in generally reduce the internal forces in the lining. And so to be conservative, even if we are not taking into consideration this, probably we are on the safe side. Please go again. For the permanent ground deformations, we generally say that this is the greatest risk for the underground structures. And in general, it is not easy to design underground structures to withstand the large permanent ground displacements. For tunnels, it is easier, but for underground structures, as we will see, it is not so easy. But even for tunnels, we have to, as we say in the next one, we have to find out other places probably, but please to the next one, Rita, if it is possible. Empirical relations, of course, are proposed for the landslides and the liquefaction as well. Go to the next one because the time is for the buoyancy again is probably the main problem that we should consider in the case of tunnels crossing liquefiable sites. And in all these cases, we say more or less, and we force the engineers to find the solution either to avoid or to take mitigation measures that should be applied in this case. And what is important here is there are some methods and some technologies, let's say, to have joints that can accommodate this longitudinal deformation of the tunnels, but this cannot be prescribed in detail in a code. We just say that in these cases where you have to face this kind of longitudinal deformations, special devices should be designed according to the way that the tunnels are constructed. And so it is something that is allowed, but the engineer has to take into consideration these issues. The next one, please. For strike slip faulting, the countermeasures are similar to the previous one and should be considered in order to minimize the consequences. Now, the estimation of the spatial distribution and attenuation of the maximum fault displacements along the tunnel, it is a very difficult issue to be estimated in a correct way. So we have to use empirical relations. In many cases, it is proposed to use 2D and 3D numerical approaches in order to simulate this evolution of the deformations along the tunnel. And this is particularly recommended and preferable for high seismic action classes and for segmented tunnels. The next one, please. I discuss a little bit the problem with the joints. We say that joints of segmented lining should be able to accommodate the permanent ground displacements along the tunnel in both sides of the faulting. Joints having special design feature and capabilities should be used in case of these cases. And again, we say, okay, but we cannot withstand this kind of solutions in case where the displacements are higher than 80 centimeters to 1 meter. And so we say that in this case, it is rather difficult to structurally accommodate the imposed ground displacement using specifically designed joints and other solutions. So this limit of 800 millimeters to 1000 millimeters is somehow the limits which is allowed to use this kind of solutions. Please, the next one. Now, for underground structures like parking stations, the main idea in the code is that the analysis should include soil-structure interaction. Pseudostatic analysis, as is described in the next presentation, may be undertaken, but it can be used only if it meets these two conditions. The distribution of the total earth pressures, static and dynamic with depth, satisfy the hypothesis imposed in the section 10, and the underground structure has limited a depth in order to fulfill the conditions for the development of earthquake earth pressures, according again to the section 10. The next one, please. Large underground structures subjected to seismic shaking may be analyzed using a two-dimensional frame spring model. Annex I provides the specifications for this. Again, the problem in this case is how to estimate springs. They should be compatible with the strains. And again, please go to the next one. We say that we may have important uncertainties with regard to the estimation of soil springs in this case. And there is a note saying that this estimate cannot be used with a certain safety for rather shallow structures, not for deep structures. And we pose at 10 to 15 meters. For ground shaking, the underground structures in high seismic actions, full dynamic analysis, 2D or 3D, with a coupled soil structure system is proposed. And ground structure properties should be simulated in a wide range of strains. Large underground structures cannot accommodate moderate to large permanent ground displacement. So in this case, we have to move the underground structure in other places when we have seismic fault failure. It is very, very dangerous, and the code is very strict about this. The next one, please. And just few comments about the culverts. What is important to say here is that these are maybe both rigid or flexible. And in general, we can use it if it is not very long. They are particularly vulnerable to permanent ground deformations. Effects of transient ground shaking may be neglected for culverts if their span is less than 2 meters. And what is very important for this, in order to accommodate the deformations of the backfill, etc., is the design of the segmented culverts. With this, I think, and with some problems that I had, I apologize for this. Thank you very much for your attention.
Thank you very much. So I think in the end, we succeeded to finalize the lecture. And yeah, I think a lot of new things were implemented. And I will shortly check the chat. There is one question from Rainer Flesch. He's asking, in NXH, the formulas of Christoph Stratos are used, which are based on sine waves. I assume in your PT, you have also discussed the possibility to use the approach of Hashash et al.
It is the approach of Assas, but it is updated and upgraded. It is not, because the approach of Assas, it is essentially for racking. Now, the new analytical formulas that are proposed are considering both racking and rocking.
Okay. There is a second question from Kostas Georgiopoulos. What CC is normally used for motorway road tunnels in Greece? So which consequence class?
I'm not sure that I can give an answer to this because this whole chapter it was open since now.
So maybe I can give a comment on that. So if we have such decisions in Germany, so usually different aspects are considered. So the functionality, so the importance, the functionality, the size, and everything. So then the traffic, the kind of traffic. So I think it is not possible to generalize it. No. And usually it is a particular decision made by the authorities.
Is more or less the same here. So yeah. There is not a unified proposal. Is case by case.
Yeah.
So it is defined in the clause when the job is offered. I mean.
Yeah. So if you have a, let's say, motorway road tunnel on the countryside, so then
yeah.
It doesn't matter.
In general, the tendency is to be considered as important structures.
Yeah. Okay.
So this is the main idea.
Okay. So I think these were the questions. So then thanks again. And then we will, no problem, we'll lead over to the last speaker.